So today we're going to talk about the intermediate value theorem, sometimes known as IVT. We're going to talk about how it's a consequence of continuity and how we can use this theorem to help us prove some things. So first, before we dive in, I want to recall your memory on continuity in general. I have the definition up here to jog your memory that f of x is continuous at a point if the limit from the left and the right approach the same point and the value actually exists at that point. So a function approaches some value from the right, from the left it approaches that same value, and the function is actually defined at this value. So then from our definition of continuity we get this theorem IVT, which states, suppose f is a continuous function on the closed interval a to b, and let m be any number between f of a and f of b, that there exists a number c such that these two properties. So I'm going to draw a graphical interpretation of this, that we have a continuous function on this closed interval, a to b. So say we have f of a down here, f of b down here. We know it's a continuous function, so we can connect those 2 points. Let m be any y value between these 2 points, f of a and f of b. Let's make our m right here, for example, but it could be anywhere on this interval. Then that means there exists this number, c, such that f of c equals your m value here. And also your c is between a and b. So really all IVT is saying is that if you know a function is continuous on a certain interval, it accepts all points in that interval. So that's helpful because it can help us prove that roots exist. So if you want to prove that on this certain function, let's call it f, there exists at least one root, we can say if we know at least one value is negative, let's say f of a, and we know another value of our function is positive, let's call it f of b, and we know it's a continuous function so we can connect the points, we know it has to hit the x-axis at this point, which we're going to call c, such that f of c is equal to 0 instead of m in this case because our m is the x-axis. But this isn't only restricted to proving roots or positive and negative numbers. You can also prove it for any m between f of a and f of b. So let's say you have a value in your function 1 at a point A, and you know your function has a value of 3 at point B, and you know it's continuous, so you can connect the points. We could prove that this function hits or has a value of 2 at some point that we're going to call C. The thing about intermediate value theorem is it's a little vague. It doesn't say exactly where C lies between A and B, and it doesn't tell you if there's more than one C. Really, this function could have hit 2 in a couple different places, or it could have only hit it at 1. But the point of IVT is really to just prove that that 1 exists, not necessarily where or how many. That's not really what we're worried about, just the fact that we can say it exists. So, besides that and the fact that it has to be continuous, those are the 2 most important things. You can only use IVT if your function is continuous. So we're going to do a couple of true and false questions here to stress the importance of continuity in your function. So the first one is a statement that says if f is a continuous function on this interval 1 to 4 with f of 1 at 10 and f of 4 at 2, then there must exist a number c between 1 and 4 such that f of c equals 5. So our m in this case is 5. So we drew a line here, and we know that our function is continuous, and we would say, yes, our function definitely hits 5 at some point C. It's important to note that this statement is only true because they said it was a continuous function. If they left out that one little word, this statement would not be true because that would leave room for a possible discontinuous function. So one more example. Given this function, IVT guarantees that f of x equals 2 for some x between 0 and 3. So, if they don't explicitly give you points, you can plug in the bounds of your interval into here and make your own points. So if we plug in 0, we're going to get 1, And if we plug in 3, we're going to get 5. So I'm going to make a guess that our function looks like this. And this statement says that our function is equal to a value of 2 at some point. So this looks like, yeah, we definitely have some value C. But this is actually false because it doesn't address the most important part of IVT, which is the fact that it must be a continuous function. This statement never explicitly says it's a continuous function, and really before you try to make any assumptions about a function, you must always check its domain. So specifically this function, x cannot equal 2, and the most important part is that that's on our interval. If they asked us between -1 and 1, we could maybe prove that, but we know, this was just a guess of our graph if we weren't really sure. This is what the graph actually looks like. I wouldn't expect anyone to know that, but I want to show for understanding purposes that this is what the graph looks like. There is a discontinuity at x equals 2, and because that's the interval that we're concerned about, IVT is not applicable here. We can't use it to prove anything because we don't have the initial condition that f is a continuous function. So this one would be false. Okay, so now that we have a basic understanding of IVT, its principles, most important properties, we can actually use IVT to formulate our own proofs, which is exciting because that's a big step in math. So this one says, use IVT to prove that f of x is equal to x cubed has at least one root on the closed interval -1 to 1. So I have a little hint on here that our goal is to prove that our function is equal to 0 at some point on this interval. This is kind of like this example we did over here in the definition. We proved it hit our x-axis at some point, and that's because we knew we had a negative value and a positive value. So for this example, before we can try and prove anything, we must always have our initial condition that our function is continuous on the interval. You must always state this initial condition before trying to use IVT. So we state that f of x is continuous on the interval. Then we can try and prove that it hits the x-axis at some point by using the values of the boundaries and plugging them into our function. So when we plug in -1, we get a -1. And when we plug in 1, we get a +1. So we'll have -1, -1, +1, +1. I'm going to assume that, or let's pretend that I didn't know what the function of x cubed looked like, and I'm just going to say, okay, I'm going to connect those points. I know that it hits the x-axis at least one point. If this was a different function and we knew it didn't only hit the x-axis at one point, you could say, yeah, maybe it hits the x-axis at multiple points. But IVT can only come to the conclusion that f of x has at least one root. And then you can add here, you prove this by IVT. So IVT, as you can tell, is a really important or useful concept of continuity to help you prove that roots exist or that your function equals a certain value. And yes, that's about it.